Okay, so let's go ahead and move on. The other thing we talked about last class was central limit theorem. Right, so that's where I take, that's that mean of the means thing, right? Where I take a sample of 30 and I find their mean. I take another sample of 30, I find their mean. I take another sample of 30 and I find their mean. So each one of these, 11.24, that represents a sample of 30 and the mean of that sample. 10.41 represents another sample of 30 and their average. 10.86 represents another sample of 30 and their average. So each one of these numbers represents the average of 30. So that's what, like, me and my friends would have given like the mean of the means. So we kind of wrap our heads around the fact that our data are means. And we're trying to find the mean and standard deviation of means. Anyway, remember central limit theorem says that these means will be normally distributed. Right? They'll be centered around the middle, the center around the mean, and then there'll kind of be fewer and fewer of them as you go further out. Even if your data is not normally distributed. Oops, wrong one. Here's the definition of it. All right, so what happens is you take every possible sample from that group. So for example, if I have the numbers 1 through 40, if I were to take every possible sample of 30 out of the numbers 1 through 40, and take the average of each of those averages would form a normal distribution. And it's hard to show you all of that, but I can show you it just from the beginning. You won't see it be a total normal distribution, but you'll see it starting to become like a normal distribution. Just with the numbers 1 through 6, and you take a sample size of 2. So I randomly have the numbers 1 through 6, and if you randomly pick them, they all have an equal probability of being picked. Right? So I have a 1/6 chance of getting a 1, 1/6 chance of getting a 2, 1/6 chance of getting a 3. Good? Everybody on board with this? It's uniform. They're all equally likely. So what I'm going to do is I'm going to take every possible combination of 2 of them. So 1 and 2, 1 and 3, 1 and 4, 1 and 5, and we'll average them. So here they are. So you can see 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. So here's the average of 1 and 6 is 3.5. The average of 1 and 5, if you average 1 and 5, you get 3. Then all the ones for 2. So 2 and 1 are already done. So 2 and 3, 2 and 4, 2 and 5, 2 and 6. So here is the average of 2 and 6. Make sense? And then the same, 3 and 4, 3 and 5, 3 and 6, 4 and 5, and then 5 and 6. The average of 5 and 6 is 5.5. So these are all the averages of every possible, combination of 2 of them. These numbers, if I graph them, you'll see that bam, you can see it's starting to become a normal distribution. You see it's just beginning to, and that's just with a sample size of 2 from a uniform distribution. Obviously, a sample size of 30 becomes a lot more like a normal distribution, right? So to wrap your heads around it again, I think it helps to think about Steph Curry. We all remember him, right? This is his one single game in red. You can have a 50-point game if you're just looking at one game. But if I take an average of 25 of his games, if I took every possible combination of 25 of his games from that season, then and I found the average of those 25 over and over again, where there's like, what, 80 games in a season? Something like that? I don't know, something like that. If I took every possible combination of 25 of them and averaged them and graphed them, it would make this blue line here. And you'll see that they're all a lot closer to the middle, to the actual average, because if I take an average of 25 games, I'm not going to get 50. Because I might get 1 or 2 get 50-point games, but I'm also going to get some 10-point games, and they're going to kind of balance each other out. So you're going to get something a lot closer. So the thing about this is, the key is, what's up with it? Instead of my standard deviation being 10, it's going to be smaller. How much smaller? I did this last time, I'll do it again. Remember, sigma x bar will be the old sigma divided by square root of n. In this case, the old sigma 10 divided by the square root of n, 25, and you'll end up with 2. That guy right there. The bigger the n, the bigger your sample size, the more canceling out happens So the smaller the standard deviation is. Here are the conclusions. The distribution will become normal the larger your n is. The mean u x bar, so the mean of the sample means, is the same as the mean. The standard deviation, sigma x bar, so the standard deviation of the sample means is the old sigma divided by the square root of n. Those are the things you need to know. A couple of things. So here's your quiz problem. I thought I had, okay. So here's your quiz problem number 3 on your quiz. Has everybody had a chance to do these?
Yes.
All right. So my mu x bar is just my mu, 36. My sigma x bar, and again, write all of this out. Don't leave off steps. Sigma x bar, well, you can leave out the sigma over square root of n if you want, but it's 7 over square root of 42. 1.08. Great. All right, and as you can see here, just some quick examples. A normal distribution, as the sample size goes up, it becomes tighter and tighter, smaller and smaller. Yeah?
Is your mu x bar always just going to be the mean, or does it?
Yes.
Okay.
Mu x bar is always just the mean.
Okay. Got
Yeah,
it.
the mean, because I mean, you know, if my average is going to be 10 minutes, if I take a sample of 25, I still expect those averages to be 10 minutes.
Okay.
Yeah, that won't change. It's just your standard deviation becomes smaller, that's all.
Okay. Thank you.
Oh yeah, thank you. So normal distribution, you can see it's still centered at the same spot, just it becomes, you're kind of more scrunched up. Uniform distribution starts off not normal distributed at all, it's a flat line, but as n becomes 10, it becomes sort of normal, and then when n is 50, it's totally normal, and the standard deviation is pretty small in there. And then, I can even take kind of the opposite of a normal distribution, a U-shaped distribution, which kind of is bowed out. And you can see when n is 10, it starts looking kind of normal, and as n is 50, it's also a really nice normal distribution there. There are some conditions, right, which you all wrote down last time. If the original variable is not normal, you need to have a sample size of 30 or more, and then it will be normally distributed. The means will be normally distributed. If the original variable is already normal, then any sample size will do. And this is your glass problem that you folks did. So here, figure out the things that you need. So I would say do this. Find your mu, find your sigma, find your, oh, first of all, is this a regular normal distribution, or is this a central limit theorem problem? So I want you to talk to your neighbors for 15 seconds and figure out why. How do you know?
Anything that's a sample of means is a central limit theorem. Yeah, so that's how we know. Oh yeah.
All right, how do you know? How do you know?
Yeah, because it involves a sample of the world.
It has a sample of 55 families. Yeah, it has an n. That's one way. What's another way you know? Probability, was that?
Probability of the mean.
Yeah, probability of the mean. So you have a probability of the mean and you have a sample, both. Those are the two things, right? You have an n. Okay, great. So I would suggest you find your mu, you find your sigma, you figure out what your n is. N is the sample size, how many you have, so this should always be a whole number. And figure out what your x bar is, your x or your x bar, the thing you're trying to find. So I would suggest you find those 4 items first, and then that will make things a lot cleaner for you in terms of figuring out this problem. So steps for this central limit theorem problem. First, find these items, and then you're going to, number 1, compute sigma x bar. 2, find your z-scores. make sure you're using, right, using sigma x bar. 3, draw a picture. And 4, use normal CDF. If you need to, you should be writing down these steps. If you need to, you should write down what the formulas are to find sigma x bar. Right, those are all things that you need. Anything you're using and having to look at to do these problems, you should be writing down in your notes. All right, so take a few minutes. If you have already done them, take a break. If not, then do this first and then take a break, and then we'll come back at 20 after. Okay, let's take a look.
Oh yeah, for sure.
So our
I didn't post this, but I'm like,
mu is 17.2. Our sigma, our standard deviation, is 2.5. Our n is 55. And then our x, you know what? I'm going to call it x instead of x bar, because technically it's what we're looking for, right? And you folks used to looking at them as x's, so we can leave it as x's. That's fine. Our x's are, in this case, they are several means. So what we're looking for is 17 to 18. So I think about these as calling x's, people will be less weirded out by them. That makes sense. So we'll call them that 17 and 18. All right, so because it's central limit theorem, the very first thing we need to do is find our sigma x bar. Sigma over square root of n. 2.5 over square root of 55 and 0.237? 337. Step 2. Find our z-scores. So my first z-score, z1, will be 17 minus 17.2 divided by 0.337. Once you find sigma x bar, use it. Don't use the old sigma, use the new one. You just found it. What was the first z-score? Negative
0.5935.
Okay. Second z-score, 18 minus 17.2 divided by 0.337, and you got what?
2.374.
374. All right, so here's the deal. We're going to draw a picture. Put in our z-scores, negative 0.59, say 35, and 2.374. All right, so then we do shape between them. And then we're going to do normal CDF. Negative 0.5935, comma 2.374. And what did you get for that? 0.715? 715? 0?
I just remembered 3 6s.
So we'll say 5-1. I don't know. I'm just gonna make something up. Okay, so here's the thing. Here's my only dilemma. On the exam, I'm totally fine with this, as long as whatever you put in matches up with what you got. However, on your homework, if you do this, it's gonna say it's wrong. And you're going to do it 3 times, and you get the same answer every time, and you're going to wonder why the blank, your homework, isn't marking it wrong when clearly it's correct. So what does your homework need you to do? Round your z-scores to 2 decimal places. Is everybody on board with that? Yeah.
So on the test, it wouldn't matter if your z-score has more than 2.
I'm okay with it, because I can make the adjustment.
Okay.
But here's the thing. If what you put here matches that, you're fine. But if you did, okay, so who did normal CDF rounded 2 decimal places? Who did negative 0.59 and 2.37? Okay, what did you get?
I got 0.7135.
7135. Okay, So if you did the first one, wrote down the top one, and gave me 0.7135, I'm going to mark it wrong because what you did and what you got didn't match up. If you did this one, negative 0.59, comma 0.237, and they gave me that answer, I'm going to mark it wrong because what you showed me, whatever you write here is what you need to put in your calculator. Does everyone understand what I'm saying? I'm assuming whatever you wrote here is what you put in your calculator, and it better match what you give me. Good? And I'm fine with whichever way you want to do it, but just make sure that it matches up. Your homework is less forgiving. It's going to want the bottom one. Good? Okay. Yeah, no. That's why I pointed it. Thank you for giving me the opportunity to point that out. Just so people are clear before they do their homework. Okay, so now you folks have got 5 minutes to do the cell phone lifetime problems. So this is on your notes, the very, very last problem on your notes, back page at the bottom. If you're not going to get the homework done 6.3 before the exam on Thursday, and you're taking the exam on Thursday, this is your last chance to practice this really, kind of. Your last chance to practice it in class for sure. So make sure you really try to sort out what these things are. And again, I would say try to figure out what your, if it's a central limit theorem problem or not. And again, you're going to try and find your mu, your sigma, your n, and your x's, whatever your x's are. All right, so two folks have here. So first of all, how do I know this is a central limit theorem problem? Yeah, probability that the mean, right? Yeah, and also there is there's 33 employees, so that's an n. So those are both the two ways that I know that. What is my mu? My mu, the average is 24.3. My standard deviation, literally says standard deviation, that's pretty straightforward, 2.6. And then my x, what I'm trying to find, less than 23.8. That's my x I'm trying to find. All right, so since I know it's central limit theorem, first thing I'm going to do, I'm going to find sigma x bar. So it's 2.6 over square root of 33. And what did you get? Nicole, what did you get?
0.4526.
4526. Great. And then we're going to find our z-scores next. So my first z-score, I only have one z-score. So my z-score is going to be 23.8 minus 24.3 divided by 0.4526. So you'll get negative 1.10 or negative 1.11, depending on what you use for your standard deviation. Either one's fine. I don't care. It's all good. And then, do a picture, right? Picture. Here's my middle left. It should be on the left side somewhere. Negative 1.1. I don't know. Negative 1.1. Who? 10. 10. Sure. We do that way. So then, Francois, you did. It's less than, so it should be shaded on the left side. So this is going to be negative infinity. Sorry, it's not right. 88. Negative infinity. So then, Francois, you did what?
Normal CPF, I think infinities of negative 1.10.
And you got
0.1357.
0.1357. And that's the number that goes inside here. 0.1357. Okay, good? All right. Okay, so the other one I want to talk about and mention is, okay, so I don't know if you folks know, but I actually got kicked out of Berkeley 3 times. That's your record. The first time was just, I wasn't ready to be a student, right? My mind was elsewhere. My mom had died. I was like focused on being a good person. So when someone said, hey, I need to go, can you take me to the grocery store? I'd be like, okay, you have class right now, but I'll study later. I'll read the book and study later, right? That's our big lie we always tell ourselves. So that night, then I try to read the textbook, and of course math books are super boring. So I'd fall asleep, and I'd be like drooling on my book, fast asleep, go to class the next day, and I wouldn't understand half of what's going on. They talk about, because math builds on itself, right? So when you miss step, then it's like you just get a little more lost, and so I just drop further and further behind. So I got kicked out the first time, and then the second time, I tried to come back, but I still wasn't quite ready to be a student. And then finally, like 10 years later, I was ready to be a student. I got my stuff done at DVC, had all my stuff together, went in, and I found out that I hate electrical engineering. Who the heck knows at 18 what you want to be the rest of your life? Right? So then my dean said, oh, you switched majors, I'll let you back in. So I switched to statistics, loved it, did it, and piece of cake, right? So, so I guess what I'm saying is I'm not saying you should drop out of school. So don't take that. That is not what you should take from this. What I'm saying is a couple things. One is that sometimes. Okay, so first thing is exam one. Okay, for some of you, if it didn't go well, you can still recover if you work hard, right? And even if you don't pass, so exam two is going to be not necessarily. It's going to be about the same level as exam one. It'll just be different. But exam two is sort of important because chapter 6, everything in chapter 6 gets built on in chapter 7, 8, 9. So it's kind of important to kind of get a handle on chapter 6. But even if you don't pass that exam, keep working hard at this because everything you learn this semester will help you build and give you something to build on so you can pass next semester. Right? So that's what I would say. Because actually you can't do XW anymore. But that's the whole point. If you folks remember in KB 705, I said that that the idea is that letting people, they took away all the prereqs for this class because the idea was failing this class is a better preparation to pass this class the second time than taking Algebra 1 first and then taking this class. So it's totally fine to fail this class. I actually have a number of students who fail it and then retake it with me, and the most common outcome is they fail it and they get a D the first time, and then when they retake it, they get a B. Because it's all new stuff. It's all new material. So there's a lot of stuff you're picking up. Standard deviations, right? Mu's, sigmas, all these things you haven't seen before. It's all kind of brand new things. So I guess what I'm saying is, one, if you didn't do well in exam 1, don't give up. Work hard for exam 2. If that doesn't go well, still don't give up. Keep working hard because you can still pass the class. And if you don't pass the class, it puts you in a better shape to pass the class next time you take it. And if you decide that really it's just not the right time for you to be in school, which it may be for some people, that's okay. Don't beat yourself up over it, right? Cut yourself a little slack and say, okay, when I'm ready, then I'll do it. Because when you're motivated and you really want to do something, it goes so much smoother. So I guess that's kind of what I'm saying. So don't give up. Oh, and I guess that's the other thing I'm saying, is don't give up on yourself, right? No matter what happens. Even if it doesn't work out, don't give up on yourself no matter what, right? Because that was kind of key. And luckily, my sister didn't give up on me, so she kind of kept me, going along, right? All right, so. You guys are awesome. We're gonna skip 6.4 for now. I'll get to it afterwards. It's not that important. Because I do want to do a little bit of review about things that are going to that I think you folks want to kind of look at to to kind of help clear your mind and kind of clarify in your mind and get them sort of set into different places. So first thing I want to ask is, what are the 4 distributions we've covered so far in this class in the last few chapters? So talk to your neighbors if you need to for 15 seconds. See how great those are.
We got the uniform distribution, binomial, normal,
standard,
yeah.
and minus. So that normal.
Use essentially, yeah, but the uniform first, uniform, binomial distribution, normal distribution. I feel like maybe it's just central theorem counts as distribution.
Okay, so someone give me one. What's one? Normal. Great. What's another one? Uniform. Good. What's another one? Binomial. Good. And the last one is a little bit weird. It's what I call the, it's discrete. Discrete probability. And I'll probably call it a discrete probability table sort of. It's the discrete probability distributions. It's the one where I give you a little table, right? The x and the probability of x. Right? Yeah, they're sort of fixed numbers.
I didn't know what that was called.
Yeah. So those are sort of the 4 different ones. So let's just take a few minutes and talk with your neighbors and try to think about everything you know about them. What do you know about them? How to find the mean? How to find the standard deviation if you need to? What do they look like? If that's an issue. How to find probabilities of them, stuff like that. So take a few minutes and try to sort out what you folks know about it. Remind yourselves of that.